Hello and welcome back. In this notebook we focus on decision trees and we go over a possible solution to the exercises when we want to get to know how a decision tree works. We look at the performance of a simple decision tree. Of course, this is a very simple model and not the most performant one, but it will illustrate a lot of the points we want to look at. We will use the so-called adult data sets that focuses on the binary classification, namely whether or not a person makes more than $50,000 per year. It's taken from the 1994 census and taken from this paper over here. So we import all our necessary libraries, and here we can see that we import a very simple decision tree classifier from scikit-learn and not an advanced one. First we read in the data, and the data are located conveniently at one of these machine learning archives, where a lot of datasets are stored. And notice that Pandas not only is able to read local CSV files, but can also directly open a web connection and download the data from there. The data file itself doesn't have column names, so we provide them manually over here. And now we take a first look at the first few rows of this dataset. So here is the index. It's just a running number from one to the last. And then the age is a number. And then we have a number of variables or features. The income here is the target variable, and this determines if it's less than or greater than 50K. So this is what we need to predict. And as you can see, all the features are a mixture of numerical variables or essentially strings. As always, when we start with a new data set, we do some exploratory data analysis and look at the variables to understand them. Conveniently, the function displayed from Seaborn can handle the text values from the data directly. We will need to convert them later on, but for now we can just use Seaborn to look at the data and get a feel. We split the color of the graph by income because this is our target variable, and we want to find out which of the variables are predictive for our feature, the income, the target variable. So we plot, for example, the education along the y-axis so that we have the labels easily recognizable because they can be written horizontally, not on the x-axis. So essentially we swap the normal x and y-axis just for readability. And then in blue we have smaller than 50K, and in orange we have greater than 50K. And we can see that education has indeed a large impact, and it behaves a bit as you would expect. If you have, for example, a doctorate or are involved in higher education or a master's degree, then you would expect to make more money as you, for example, leave college early. You can also look at the marriage status and how this influences the distribution of the income or other variables such as gender, and here they only distinguish between male and female and nothing else. You can also look at race, how this is distributed, and unsurprisingly there's a large disparity here as well. For example, we can also look at the occupation, so which job essentially pays well, and we can also see that here we would expect that higher jobs pay better. For example, managerial jobs tend to pay a lot better than other jobs on average. We can also look at continuous variables, for example, the hours per week worked, and how this affects the income. And now that we've understood the behavior of the variables a bit, we need to improve the variables such that we can use them for machine learning. In particular, if we scroll back, remember that all these values are strings, so we need to convert those into a format that our machine learning classifier can work with them. So we do this as a first step. First of all, for all these categories, we take as an example the work class variable. We look at which unique values occur. So these are those, and put them into a list. So this is what this does. with unique, we get all the unique values into a list returns as a Python list, and then we change the data type, right? So we put this as a categorical variable, and we do the same thing for the others as well. Let's see if this worked, right? And then we have now a categorical variables where these are the categories. And because they are not ordered, we put this in here. And then we convert those into numerical values, and a code is assigned to them. It's essentially a number. Now that we converted all the columns with the data type, with the strings into a category data type, we select all of them. So this is what we've done above. And then we convert the strings and the categories to their numerical values. And this is where we use the lambda function, and the apply function. So let me walk you through what this does. So we have here the data frame, the pandas object that holds our tabular data. This is where we have converted already the categories. And now we use the apply function, and the apply function essentially works on each element of this data frame, for example, each row, and then each variable in the verticals. And the lambda function is, as we remember from Python, it's a function, and then it replaces x with its code. So it takes a little while to get used to this kind of syntax, but it's very efficient because it avoids that we write the loops ourselves. And this is much more speedy and doesn't take so much time when we work with large data sets. Here it probably wouldn't matter so much, but if we have a large number of data points, using the apply function allows us to use the optimizations that are built into the pandas package. And this is the result. As you can see now, all the data types are numerical, apart from the income, which we haven't transformed yet. Now, this is what you can do as a little exercise. Remember here that you use apply function and the lambda function again, and now we want to convert the target income into 0 and 1. So we have 0 if x is smaller is this string, and otherwise it's 1. So here you can see again that we could of course have looped over this data frame ourselves, but using the apply lambda method allows us first of all to do this in one step and also very efficiently. Now then, to follow best practices, we need to keep the test and training data separately. We use the convenience function here from scikit-learn to do this and keep a test size of 1/4 of all our data points. And we use a very simple decision tree here. We set the random state to 0 to make the model more deterministic. You can look it up in the documentation. And since the data set is quite small, the default values will result in a very good model, but it will also easily overtrain. So we increase the minimum number of samples in each leaf to reduce the flexibility and prevent too many splits and prevent a little bit of overtraining. So we keep at least 10 leaves there. Now we define the classifier and call the fit method, passing the training features. This is xtrain and the labels ytrain. And the exercise was to do this. Right, so we can take the model. This is an instance of the decision tree classifier. We define our random state and add here the parameter min leaves and then call fit. And scikit-learn also provides us with a neat method to plot the resulting tree. And as you can see, although it's a very simple classifier, the model itself is in principle something we could understand, but you can already see from the complexity in practice this will be very difficult. Now we look at the predictions. We call model predict and model predict power for the validity or the score of each class. That returns an array for each prediction. And since we only have 2 classes in the example, the first value for each prediction is the first class and then the other one. Of course, if we have more classes, then we have more numbers here. So for convenience, we append the predictions and the 2 labels to a copy of our test data set. So this allows us to look at the values and also all the features and everything in one single data frame. So this is what we do here. We copy over the data set, call the predict model and the predict probar, and then at the end we append these values as new columns. So this is what our resulting data frame looks at. We have here the target variable y, the prediction, and the probability. Now we need to see how well our classifier performs, and this we can, for example, do with the confusion matrix, and scikit-learn offers a nice way to plot this. So we create a confusion matrix object. We give it the test data. Here we use the independent one and the predictions, and then print a color-coded matrix of this. And as you can see, it's fairly accurate. You can also get a summary report with the most relevant metrics like precision and recall. And importantly, we can do an ROC curve. Here, this is where we need the probabilities, and the curve is constructed by getting subsequent thresholds throughout these scores. And then we compare how well we perform against random guessing. Random guessing, remember, would be along the diagonal line, and the closer our classifier comes to this point, the better it is. So we can see that even the single decision tree works fairly well on this dataset.